Hi, this is Ryan from Roots of Unity, and today, as a part of our polar coordinates series, we're going to discuss curve sketching. Now, let's start from the basics. So, let's do points, lines, and circles. A point is the most simple of all. Just make sure you know what coordinates the question is showing. Is it an XY format or R theta format? Also, keep in mind that the angle is counted as positive in an anti-clockwise direction. If you see an angle that is negative, go clockwise. Next off, we have a simple line where only the angle theta is mentioned. In this case, it is constant line starting from the pole and extends as much as the range allows. Now, when only the value of the radius is mentioned, it's pretty obvious that it will lead to a circle. If you've worked with locus before, this might be familiar to you. It's pretty simple. Now, let's move on to trigonometric equations. If you remember what you learned in the last video, this one should be quite obvious. Just substitute r cos theta with x and you're good to go. It's going to be a line with x equating to the constant a. The same applies to the second graph, where we replace this with y. Now, these two are pretty fundamental when it comes to polar curve sketching. These are the graphs for cos theta and sin theta. Now, keep in mind the range for these graphs. If you were to take the range here as 0 to pi, the latter half would give us a negative radius, as we can see in this Cartesian graph. Therefore, we took the range such that it covers the positive radius, and hence we end up with this circle, which has its center on the x-axis. You might have noticed the pattern here already. If you haven't, the sine graphs basically follow the same route as the cos graphs, but rotated. They undergo a 90-degree anticlockwise transformation. We'll elaborate on that in a bit. Now, you can see that for the r sin theta graph, we took the range from 0 to pi accordingly. Now, let's take a look at the general format. Here is r equals to 2a cos theta. This would be a circle with center as a0 and a radius of a. And of course, the general format for r equals to 2b sin theta is similar, but this time the center is 0, b. I think we've had enough of circles, yeah? Now, let's take a look at something different. Here, we have the curves for sin 2 theta and cos 2 theta. The shape is a lemniscate. You'll notice that the angle between the two curves is pi by 4. Firstly, recall how in a general case the relationship between the two curves would be an anticlockwise transformation with an angle of pi by 2. Let that be alpha. In this case, alpha equals to 2 theta. We insert that in the equation, leaving us with a value of theta as pi by 4. Similarly, the difference between sin 3 theta and cos 3 theta would be, you guessed it, pi by 6. We'll practice how to draw a similar curve at the end of this video. Don't worry. The shape you see here is called a rose. Pretty cool, right? Let's look at some special cases first. For r equals to a theta, we use assumptions. We know that for small angles, sin theta equals to theta. Hence, as theta approaches 0, the curve reaches an asymptote at y equals to 1. For r a equals to theta, r increases gradually, forming a spiral. It's pretty self-explanatory. As for this exponential equation, the curve starts from a radius equating to a, when theta equates to 0. Now let's take a look at the cutest graphs of them all, cardioids. Hertz basically. There's a bunch of basic formats, and they'll help you understand these graphs really quick. At 0 degree, the radius is 2 as cos theta equals to 1 and these add up together. At 90 and 270 degree, the radius is 1 since theta equals to 0. And theta equals to 180 degrees gives us a cos theta value of minus 1, which cancels out the 1 and leaves us with a radius of 0. This similar pattern follows when it's 1 minus cos theta. And for the sine graphs, it's transformed 90 degrees anticlockwise, of course. Here, the maximum is 3 plus 3 equals to 6, located at theta equals to 90 degrees. The easiest way to do these graphs is to plot the points at the significant angles, such as 0 degrees, 90, 180, 270, and 360. The shape of the curve becomes obvious afterwards. You can see some more examples here. Now, when B is greater than a part of the curve produces a negative radius, which isn't shown in the graph. These shapes are also called Nimasons. The term comes from a Latin word meaning a snail. Be sure to try drawing these curves yourself. A good practice if you have time is to always map out the points manually. You could use this as a double check-in strategy after sketching the shape of the curve. Try to include theta equals to 0 or 2 pi in your table. You could draw lines like those as well as circles of different radii to help plot the points. Enough chit chat, let's attempt an example, shall we? Time to sketch the curve r equals to 6 sine 3 theta. Here's a handy tip for figuring out which values to calculate. Let's start from alpha equals to pi by 2 again. This time, alpha stands for 3 theta. So we insert that and find the value of theta to be pi by 6. Then, with increments of pi by 6, we take values of theta for which we will calculate the radius. Here I've already done it for you. Now it's time to plot the points. It goes over here, and there's the 6, 0. Oh, as you can see, there's negative values of r. We're going to ignore those. After plotting the points, it's pretty obvious that the curve takes the shape of a rose. If you still feel unsure, calculate values within a specific interval and check if they're increasing or decreasing accordingly or not. And that pretty much covers the basics of curve sketching. I looked over the general shapes so that you remember them well and save yourself some time. I will always recommend calculated values and trying to plot the curves on your own. I hope this video was informative. See you soon!